Alrighty, hopefully you have tried example 9 and example 10. I'm going to go ahead and pick up there. So I've got cosine x and cosine 2x, sine x and sine of 2x. They don't have the same values right here. These two have 1x and these have 2x. So I'm going to use double angle formulas. Now what I know about sine of 2x is that there's only one double angle formula. It's this one right here, right? The 2 times sine x cosine x. For cosine 2x, there are several to choose from. I'm going to pick the 1 minus 2 sine squared x. Like I said, you have 3 options to choose. So over here, I definitely have to do the distributive property. So I've got cosine x minus 2 cosine x sine squared x plus, back here I'm multiplying all of that together, not the distributive property because there's no plus or minus sign in the parentheses. We're just multiplying it all together. So I have 2 sine squared x cosine x and then equals 1/2. Oh, good news. Look at these two. They both have a 2, they both have a cosine x, they both have sine squared x, but one is a positive 2 and one is a negative 2, and that means they're like terms and they're going to cancel each other out. Woohoo! So we have cosine x equals 1/2. So again, we want very specific domain from 0 to 2 pi. This is going to occur in quadrant 1 or quadrant 4 because those are the only 2 places where cosine is positive. So in quadrant 1, we would get an x coordinate of 1/2 at pi over 3. And in quadrant 4, we would get an x coordinate of 1/2 at 5 pi over 3. And those are going to be the only 2 solutions that we have for example number 9. All right, example 10 says to use a double angle or a half angle formula to solve. Again, we have a specific domain. We're only going to be going around the circle one time. So let's see. Well, clearly this is a half angle, so we need to go back to the half angle formulas. And for tangent, there are 2 different half angle formulas. I'm going to go with this one, 1 minus cosine x over sine x. So I'm taking tangent of x over 2. I'm replacing it with its half angle formula. Now you notice that I've got, now remember the other one was sine x over, and then it had a couple of terms in the bottom. I like this one better because there's just this sine x in the bottom instead of having multiple things in the bottom. That's why I chose this one. Remember we did a problem in the last video where we had a denominator and we wanted to get rid of it. How did we do that? We multiplied both sides by the common denominator. So for this particular problem, the common denominator is just a single sine x. Now over here I have to distribute it. What happens when it gets multiplied times this first term? Well, the sine x's cancel out, so we're left with 1 minus cosine x. What happens here? Sine x times sine x turns into sine squared x. On the other side, you still have 0. So the issue now is there's no GCF, and they're 2 different trig functions. So this goes back to Pythagorean identity. What can you plug in place of the sine squared x? 1 minus cosine squared x. And now I have to take the minus sign that was in front of the sine squared x and distribute it. So I have 1 minus cosine x minus 1 plus cosine squared x. All right, well the 1 minus 1 cancels. And so I'm left with a negative cosine x plus cosine squared x. I'm going to rewrite that as cosine squared x minus cosine x. You don't have to rewrite it, but I like the way that it looks better because I like the quadratic to come first. And I have a GCF of cosine x. So if we take that out, we're left with cosine x minus 1. So now we can take each factor and set them both equal to 0. Now this one's already set equal to 0. Let's take this one and get cosine x by itself, and now we have cosine x equals 1. Now remember, we are in a specific domain. So where would cosine x be 0? Again, I'm going to just go back to that graph of cosine. It's going to get us a y value of 0 at those two locations. And where are those? Well, one is pi over 2 and one is 3 pi over 2. So those are the two solutions that come from this factor. Second factor, we take a look at where would we get a y value of 1? Well, it occurs right here and right here. What's the problem with this one? That one is at 2 pi, which we're not allowed to include because we don't have the bracket. Remember, the parentheses means you don't get to include that one. So the only one here that we get to include is the 0. So those are our 3 specific solutions for example number 10. All right, we're getting closer to being done, y'all. So here it says, so far, all the equations we've solved have had solutions like pi over 4, pi over 3, 5 pi over 6, and so on. In other words, they've had solutions that came from the unit circle. And sometimes that doesn't occur. Now, in the last lesson, in 7.4, we did have to use the calculator a little bit, and I think that's probably what's going to have to happen here. So first of all, I'm going to try a sum and product chart. Now, this is like a 1 tangent squared x minus 1 tangent x minus 2 equals 0. Remember when we factored before, I would call the tangent x w or whatever you want to call it. If you feel comfortable with going straight into sum and product chart, let's do it. What's our sum? -1. What's our product? -2. What numbers are going to work? We need a -2 and a +1. We're going to put them both over our leading coefficient of 1. Now, normally, here's where we would say x minus 2 onto x plus 1, but we're not dealing with just an x. We have a tangent x, so this is where we're going to say tangent x minus 2 and tangent x plus 1. So if you needed to change it to have a different variable, you can. For some people, visually, that really helps them out. If you feel comfortable with just jumping straight into factoring, that's fine too. I will let you decide which one you feel more comfortable with. So now we're going to take each of those factors and we're going to set them equal to 0. So for the first one, we get tangent x equals 2. For the second one, we get tangent x equals -1. I'm going to start with this one right here. Now notice they didn't give us a specific domain, so this is where we want to say, okay, what could it be ever? This is where you might add the pi k or the 2 pi k depending on your answer. Well, where would tangent give us a negative value? That would occur in 2 or 4. Now notice that those two quadrants are exactly 180 degrees apart. So that already leads me to thinking I'm going to add pi k because that would be adding like 180 degrees. So where in quadrant 2 can I get a tangent value of -1? Again, you got to know your unit circle, but that would be at 3 pi over 4. And if I add pi k to it, that takes me to 3 pi over 4 is the quadrant 2 answer. If I add pi k, it takes me to quadrant 4. And then if I add another pi k, it takes me back to 2. And if I add another one, it takes me back to 4. So this is one of the solutions. But let's look over here where we have tangent x equals 2. Now, hopefully you guys have not forgotten the graph of tangent. Remember, you got these asymptotes and it crosses through the origin and it looks something like this. 2 is not a value that we just know what that is. It's not on the unit circle. It exists because tangent has a range of all real numbers, so it can be 2. We just don't know what it is. So here's where I need to inverse tangent on each side because I don't know that value. So I'm going to come over here to my calculator. I'm going to do inverse tangent of 2. And we're going to use 2 digits behind the decimal point. So I'm going to do 1.11. All right, so I'm going to say x is approximately 1.11. All right, let's talk. We have tangent being 2. Where does that occur? Well, that occurs, and I should have said this a minute ago, quadrant 1 is where it could be positive, or quadrant 3 is where it can be positive. Again, notice quadrant 1, quadrant 3, they're 180 degrees apart. So I'm going to add pi k so that I can get back and forth from one quadrant to the next. And so those would be the two solutions for number 11. All right, number 12. I don't know why this is a 5. Let's make that a 2. We don't ever really do it to 5 digits behind the decimal point. Okay, I'm talking to myself, sorry. Solve. Use a calculator. We have a specific domain from 0 to 2 pi. Here we go. What are we going to do? First thing we're going to do is add 2, and then we're going to divide by 3, and then this is where we go, oh, that's not a value from the unit circle. So what do? We inverse sine each side. So this is what we want to plug into our calculators. So I'm going to inverse sine of 2/3, and we're going to do 2 digits behind the decimal point, so we're going to turn that into 0.73. All right, so let's talk for a minute, because this problem is different from this one in that we have a specific domain. Where would you get a sine value that's positive? You would get quadrant 1 or quadrant 2. So I'm going to draw a little picture here real quick for a moment. Remember in 7.4 I did this too. This is 0, this is pi, otherwise known as 3.14. This is pi over 2, which is 1.57. This is 3 pi over 2, which is 4.71, and then we end back here at 2 pi, which is 6.28. Now the answer that we just came up with is 0.73. That's our quadrant 1 answer. Also represents the reference angle. So this reference angle, let's just say that that right there is 0.73. How do we come up with the angle value in quadrant 2? That means this distance is also 0.73. So remember, I have to start here at 3.14 and subtract that 0.73. So I'm going to do 3.14 minus 0.73, and now I have a quadrant 2 answer of approximately 2.41. So we took our quadrant 1 answer, which was also a reference angle, and we used that reference angle, which just means the fastest distance to get back to the x-axis, and we found what it would be in quadrant 2. If we went backwards by 0.73, that told us what our other value is. So we have a quadrant 1 answer and a quadrant 2 answer. So you see in this section, we are basically doing review of 3 chapters all in one. Unit circle, identities that we used a lot, all these formulas that we've done in chapter 7, all of this is coming to a head in this section. All right, so 2 more examples, we're almost done. I know it's a lot. Here we go. Okay, so example 13. We have 3 sine x equals 7 cosine x. Now here's an issue. I could subtract everything and move it over to one side. When I do that, I don't have a GCF. I'm not going to be able to factor. I can't use a Pythagorean identity because those both have the sine squared x and the cosine squared x, and neither of these have the squared. So what other option could we have? I'll tell you what we could do. I'm going to divide by cosine x, and you might be wondering, why are you going to divide by cosine? Because I know that sine over cosine turns into tangent. So let's change it so that we just have a single function instead of having 2 different functions that we can't turn into one another. And then next I'm going to divide that 3 over, and I have tangent of x equals 7 over 3. Again, this value does exist if you remember the tangent graph, but this isn't something on the unit circle. So this is where I got an inverse tangent on each side, and then we're going to use a calculator. Now before I use a calculator, let's talk. Where would this exist? Well, I get a positive tangent value in quadrant 1 and in quadrant 3. And again, those are 180 degrees apart. So if I can find quadrant 1, then all I have to do is add pi to get to quadrant 3. Now I want to show you these directions real quick because I kind of skimmed over them, but I didn't really talk about it. Letter A says find all the solutions. So you do not have a specific domain. Letter B, we do have a specific domain. So it's kind of like they took directions from two different problems and put them in one. We're going to have two different sets of answers. So first, let's use a calculator. So we got inverse tangent of 7/3. Okay, I'm getting, what, 1.17? Does that sound right? 1.17, approximately. That's a quadrant 1 value. How do I get to quadrant 3? I add pi. So I'm going to put add pi k. That is my answer for letter A, because that's how I could, I'm in quadrant 1, I add a pi, that takes me to quadrant 3. I add 2 pi, it takes me back to quadrant 1. I add 3 pi, it takes me back to quadrant 3. So you see how if we add multiples of pi, it takes us back to those two quadrants. That's finding all of the solutions ever, ever, ever. But for B, we specifically only want the solutions that are within that going around a circle one time. So we already have our quadrant 1 answer, 1.17. Now I need the quadrant 3 answer. So I'm going to take my 1.17 and I'm going to add 3.14 to that because I'm adding pi to get to quadrant 3, and that turns into 4.31. And those are my two specific answers if I were to go around the circle only one time. So hopefully you see the difference between those two. All right, last one, y'all. I know this has been a lengthy one. Let's start by getting rid of that 2. I'm going to divide it on over. This one's pretty similar to the last one, right? So we need to inverse tangent, right? So I have x equals inverse tangent of 13/2. So let's use our calculator. Inverse tangent of 13/2. Did I plug it in right? Yeah. All right, I'm getting what? 1.42? All right, 1.42. That's a quadrant 1 answer. Now this can occur in quadrant 1. Where else is tangent positive? Well, if you were paying attention in the last example, it's also positive in quadrant 3. So how do I write all of my solutions? Well, that's easy. Plus pi k. That takes you from quadrant 1 to quadrant 3 and back to 1 and back to 3 and back to 1 and back to 3, and we could keep going forever on that. Letter B, we want the specific solutions just around the circle one time. So we already have quadrant 1 answer. Now we need quadrant 3 answer. So we're going to add 3.14 to that answer we had a moment ago, and that's going to turn it into 4.56. All right, so before I sign off on this video, I just want to say that I recognize that this section is a lot, which is why we've spent in 2 days of homework on it instead of just 1. I would like you guys to give me feedback if there's something that you're struggling with. Please shoot me an email if we need to do an additional extra Zoom session. I don't have a problem with that, but I do need feedback so that I know from y'all what it is that you want to do, because I've planned a Zoom session for Friday, but I don't have a problem with having one on Thursday also. I would actually probably really like to have one both days, but I'm not going to assign it if no one's going to show up. So y'all send me feedback and let me know if you want one for Thursday. I don't have a problem doing it, but we definitely have one for Friday because Monday you guys have a quiz on 7.4 and 7.5. The good news is once that quiz is over, we're going to just work on some review work for a day or so before we have the chapter 7 test. So give me some feedback. Let me know how you guys want to keep going with this, and I will see you soon on a Zoom session.